Okay, section 4.3. Homogeneous linear equations with constant coefficients. So these are linear equations, right? Constant coefficients means instead of having like ai of x as your coefficient function, you just have an ai, right? It's just some number in front of every derivative. These are pretty easy to solve. If you can factor a polynomial, you can solve a homogeneous linear equation with constant coefficients. And remember that homogeneous means it equals 0 on the right-hand side. So here's how we're going to start. Second order equations. Factoring quadratic polynomials is basically the name of the game here. Factoring quadratic polynomials. So we start with a general form second order linear homogeneous equation. These look like ay double prime plus by prime plus cy equals 0, where a, b, and c are constants, and it's, I mean, we have to assume that a is not equal to 0, I guess, right? A is non-zero. So I know the answer already, but let's just guess. Let's just guess what should happen, right? Since these are all constants, it kind of looks like, well, okay. Just, this is a guess that you would naturally get to if you spent a lot of time looking at differential equations, okay? But since I know the answer already, we're just going to start here with this guess. So what if y was equal to e to the mx, right? If y was equal to e to the mx, then the second derivative of y would be m squared e to the mx. The first derivative would be m e to the mx, and y is just e to the mx. So when you plug in this y into this differential equation, you get this. And we can factor out all the e's, right? They're all the same term. So this can come out front, up here. And we get that e to the mx times am squared plus bm plus c equals 0, which means that either this equals 0 or this equals 0. And since e to any power is non-zero, right, it must be the case that this equals 0. Right, since e to the mx is non-zero for all x, it must be the case that y equals e to the mx is a solution if and only if this is 0. This is called the auxiliary equation, right? Notice it's the same coefficients, a, b, and c. A, b, and c. And instead of having y double prime, you have m squared. Y prime, you have an m. And no primes, you have just a 1. After some work, we get it 3 equations, basically, right? Sorry, three cases, not 3 equations. The first case is that you have distinct real roots of this auxiliary equation. Distinct real roots. In this case, if you have 2 distinct real roots to this auxiliary quadratic, your general solution is constant e to the first root plus constant e to the second root x. If m1 and m2 are repeated real roots, so like for example, the roots of this polynomial might be like -2 and -2, -2 twice, right? In that case, excuse me, we have the general solution is c1 e to the m1x plus c2x e to the m1x. So we add an x to the second term to make it linearly independent. Because remember, the whole thing last section was, in order to find the general solution, you need a linearly independent set, right? A fundamental set of solutions. So in this case, m1 and m2 are both solutions, and together they span the space of all the solutions. Down here, M1 and M1 span the same space, so to make them linearly independent, we add an X in front of one of the E's. That makes these linearly independent, right? Adding this X makes these two linearly independent. And last but not least, if M1 and M2 are complex conjugate roots, so for example, if our thing looks like M squared plus 1 equals 0, right? Then in that case, your roots are, what are they? Minus I and plus I are your two roots, plus and minus I. These are complex conjugate roots, right? Complex conjugate roots. They come in this form every time. Since we have a quadratic polynomial with real coefficients, we know that any complex solutions come in conjugate pairs, and they always look exactly like this. Some real number alpha plus beta I, and then some real number alpha minus beta I. They always look just like this, every single time. And in this case, the general solution to the homogeneous second order linear differential equation is constant e to the m1 plus constant e to the m2. And using Euler's formula, which says that e to the I theta, right, this part, e to the I theta equals cosine theta I sine theta, we can get the general solution looks like this. So you get e to the alpha x, right? Remember, alpha is this number here that shows up in both of the complex conjugates. And then you get c1 cosine beta, c2 sine beta, right? So you kind of ignore this plus minus sign down here. But you just get the beta and the alpha showing up, right? The alpha and the beta just show up in the solution. Let's do an example. Here's one. 2y double prime minus 5y prime minus 3y equals 0. Pass the auxiliary equation, right? This is the first step every time. Whenever you see a linear equation with constant coefficients that's homogeneous, the first step, well, honestly, even in the non-homogeneous case, the first step is to pass to the auxiliary equation. Pass to the auxiliary equation. 2m squared minus 5m minus 3 equals 0, right? So you just replace however many derivatives there are gives you a power of m, right? So 2 derivatives, m squared, 1 derivative, m to the first, no derivatives, m to the 0, right? This is technically 2m squared minus 5m to the first minus 3m to the 0, right? This is technically what's going on here. So just remember, every derivative on a y gives you a power of m, and no derivatives gives you no powers of m, gives you an m to the 0, right? Now we got a factor. You can use the quadratic formula if you like. That one's repeatable, right? It says that m equals negative b plus or minus the square root of b squared minus 4ac all over 2a, right? That's the quadratic formula. That will give you your two solutions, m1 and m2, right? Every time by looking at this plus minus. Or if you know how to factor, either by grouping or just by factoring a quadratic polynomial by like guess and check methods. Do it however you like. So anyway, we factor this. 2m plus 1, m minus 3. That tells us that m equals negative 1/2 or m equals 3. This is distinct real roots, right? So we're in case 1. Distinct real roots. Which means my general solution is constant e to the m1x, constant e to the m2x. Okay, let's go again. Y double prime minus 10y plus 25y. M squared minus 10m plus 25. Factor it. M minus 5, right? This is a perfect square. Since this is a repeated real root of 5, right, m1 equals m2 equals 5, positive 5. To get the general solution, you take c1 e to the 5x plus c2 x e to the 5x. Okay? Next one. Y double prime plus 4y prime plus 7y equals 0. Pass the auxiliary equation. The factors of 7, if you want to try to factor this, are 7 and 1 or negative 7 and negative 1. Neither of those are going to add up to be positive 4, which means this is probably going to be complex solutions. Excuse me. But it could be more complicated, but most likely it's going to be complex, right? We pass to the quadratic equation. M equals negative b, right, negative 4, plus or minus 16 minus 4 times 1 times 7, which is 21. B squared, 16 minus 4 times 7, yeah. Sorry, 28, not 21. All over 2a, which is 2. So when we get down here, we do the little algebra thing, and we get to alpha equals negative 2 and beta equals root 3, right? Alpha, beta. Then we can just cut to the answer, right? I know alpha and beta, right? Alpha and beta. So I get yg equals e to the alpha x, c1 cosine beta x, c2 sine beta x. If you have a higher order polynomial, you get a similar process. But now the auxiliary equation looks like this, right? It's an nth order polynomial to factor. And factoring big polynomials is, it's a thing. It's a thing. Look up the rational root theorem. Look up synthetic division. Look up polynomial long division. Right, it's going to be a thing where you have to factor this completely as far as you can. Excuse me. If all the roots are completely distinct, all n roots are distinct, it's really easy, right? You just do the thing we did last time, where you take c1 e to the first root, c2 e to the second root, c3 e to the third root, all the way down to cn e to the nth root. Damn. If you repeat m1 k times, I'm sorry for me yawning and I've got sinuses. It's pretty rough. If, say, m1 has multiplicity k, then you just need to add x's like you did before, right? But you start with c1 e to the m1x, and then you add an x, and then if it was repeated again, you'd add an x squared, and if it was repeated again, you'd add an x cubed, and you go all the way up to x to the k minus 1 e to the m1x, right? And then the rest, if they're all distinct, look like how they did before, right? ck plus 1 e to the k plus 1x, e to the mk plus 1, Okay, rational root theorem. So basically what I mean to say is, if you have complex conjugate roots, right, you'll have that in here somewhere, right? Complex conjugate roots could be in here somewhere, but every time you repeat a root, like if it's repeated 4 times, you would just have it 4 times, but with an extra x in each term, right? You go x, no x, x squared, x cubed. Okay, the rational root theorem. If you have a rational root, right, rational number root, m equals p over q of the polynomial an all the way down to a naught 0, then p has to divide this and q has to divide this, right? The numerator has to divide the constant term, and the denominator has to divide the leading term. Here's an example. Y triple prime plus 3y double prime minus 4y equals 0. The auxiliary equation in this case is m cubed, right? Because for each derivative we get a power of m. M cubed plus 3m squared. There's no y prime, so we're going to have plus 0m minus 4 equals 0. Now, your leading term is a 1. Your constant term is a negative 4. The factors of 4 are 4, 2, and 1, and the factors of 1 are 1. The rational root theorem says then the possible roots are the factors of a naught divided by the factors of a n, right? So it's plus or minus 4 over 1, plus or minus 2 over 1, plus or minus 1 over 1. So these are my possible rational roots, right? So plus minus 2, plus minus 1, sorry, what am I saying? Plus minus 4, plus minus 2, and plus minus 1. These are my possible rational roots. Test the easiest ones first. In this case, these are the easiest ones, right? M equals 1. If you plug in 1 into this equation, you get 1 cubed is 1, 3 times 1 is 3, minus 4, 1 plus 3 minus 4 is 0, which means m equals 1 a root. Which means m minus 1 is a factor, right? This is the, what do they call this? Is this just the root factor? I think it's called the factor theorem. Right? If you have a root of the polynomial, then m minus that root is a factor of the polynomial. Okay. Now we need to know how to factor m. We need to know how to factor m minus 1 out of this polynomial. Okay, that's where synthetic division comes in. If you're dividing a big long polynomial by a linear term, right, x minus c, then there's this thing called synthetic division. Okay, go look up like a Khan Academy video on synthetic division. It'll do a better job than I do here. But the basic idea is you're dividing this big polynomial by this linear polynomial. The only thing that's really going to change is the coefficients, right? So what you do is you start by copying the coefficients into these spots, right? You copy the coefficients into this first row of the synthetic division. And you got to make sure you add in any zeros, right? You got to add in any zeros that are missing. So like if an minus 1 was a 0 here technically and it didn't show up in the polynomial, you still need to add a 0 here. Right, so if we look in our example, right, there's this 0m term, so we got to be sure we add a plus 0 to the fourth spot. And then if you're dividing by x minus c, you put a plus c right here. So it's the opposite sign, right? If it's minus c here, you put a plus c here. If this was plus c, you'd put a minus c, right? And then what you do is you drop down the first coefficient, straight down. And then you multiply c times an, and you put that here, right? So it goes like, here's the algorithm, right? You drop down the an, and then it goes c times an goes here. And then you add these two up, right? So you get an minus 1 plus can, that goes here. And then you multiply c and put that to the next spot. And then you keep going. You keep adding. You get a new number. You multiply c by that number and you stick it in the next spot, right? You just keep ping-ponging along. And then eventually you'll get to the last step where you multiply c times whatever ends up here and put that here. And then you'll add a naught and that up to get the remainder, right? To get the remainder. And the important thing is that if x minus c is a factor of this, if x minus c is a factor of this, then you'll get a remainder of 0, right? So the way this works is, now that you have this division down here, right, you can write f, which was this, you can write f, which was this before, as x minus c times an xn minus 1, this xn minus 2, dot, 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 whatever, no x's, plus remainder. And if c is a root of f of x, then r will be 0. In this case, you get f of x is factored into the linear term and the rest. Let's do synthetic division here. So we're going to divide m cubed plus 3m squared plus 0m minus 4 by m minus 1. Since this is minus 1 here, we put a plus 1 here. And then we copy the coefficients, right? 1 goes to 1. 3 goes to 3. There's a 0 here somewhere. It goes here. Minus 4 goes to minus 4. Okay, then we start the algorithm. The 1 drops down. 1 times 1 is 1. That goes here. 3 plus 1 is 4. 1 times 4 is 4. That goes here. 0 plus 4 is 4. 1 times 4 is 4. That goes here. Negative 4 plus 4 is 0. Remainder of 0. I knew this was a factor already. So now I can write m cubed plus 3m squared minus 4 as m squared plus 4m plus 4. Right? This is my new polynomial here. This is now m squared, m, and no m, times my factor, m minus 1. And I can factor this, since it's quadratic, into m plus 2 squared times m minus 1. So, now that we've factored our auxiliary polynomial, so this is our original auxiliary polynomial, right? We've completely factored it into m plus 2 squared, m minus 1. Now, that means we have m1 equals negative 2, m2 equals negative 2, and m3 equals positive 1, right? We've got a double root and a root. So to write down our general solution, we just do c1 e to the negative 2x plus c2 x e to the negative 2x, where this is the repeated root. And then we tack on c3 e to the 1x, since that was just a normal root. Also, if you can find this as a root just by looking at it, then that's fine too, right? Okay, let's try again. Fourth derivative plus 2 times the second derivative plus no derivatives equals 0. Convert it to the prime notation, because it's a little easier to see. The auxiliary equation is m to the fourth plus 2m squared plus 1 equals 0. This, you can make a substitution. You can make a substitution that u equals m squared. And in this case, you'll have u squared plus 2u plus 1 equals 0. Right? You can think about m squared as an object, and then you can factor this into u plus 1 times u plus 1, right? And then you go back to m squared. So we've got m squared plus 1 all squared, right? These factor into plus minus I, right? So we get m1 equals I, m2 equals negative I, m3 equals I, and m4 equals minus I, right? I've got plus minus I are repeated, basically, right? So I've got alpha equals 0, beta equals 1 twice, right? Twice. So I get e to the alpha x, c1 cosine beta x, c2 sine beta x, plus it's repeated, So I add an x, e to the alpha x, c3 cosine beta x, c4 sine beta x, right? Notice that my constants are all different. These are all different constants. No x, added an x. Simplifying it down, e to the 0x is just 1, right? This is just 1. So you get c1 cosine x, c2 sine x, plus c3 x cosine x, c4 x sine x. This is my general solution. And this should be a function of x. Okay, example number 5. Triple prime, double prime, 1 prime, no primes, cubed, squared, first, m to the 0. Factor by grouping doesn't work, unfortunately. But since the degree of the polynomial is odd, it's a third degree polynomial, and we know that the complex roots come in pairs, we are guaranteed at least one real root. So the rational root theorem says any rational root should be factors of this divided by factors of this. So we list out the factors of 4. We list out the factors of, this should be factors. Factors of 4 are 1, 2, 4. Factors of 3 are 1 and 3. So the possible roots are 1 over 1, 2 over 1, 4 over 1, 1 over 3, 2 over 3, 4 over 3. With pluses and minuses. Now we just go through, start checking. M equals 1, doesn't work. M equals minus 1, doesn't work. M equals 2, doesn't work. And you just keep trying things. You just keep on trying. And eventually you'll get to m equals 1/3. And that does work. Thank goodness, right? Thank goodness. Which means m minus 1/3 is a factor, right? Since plus 1/3, since m equals plus 1/3 is a root, that means m minus 1/3 is a factor. So we take the opposite sign, put it right here. We copy down the coefficients, which are 3, 5, 10, and negative 4. We run our algorithm, right? Drop down the 3. 1/3 times 3 is 1. Put that here. 5 plus 1 is 6. 1/3 times 6 is 2. That goes here. 10 plus 2 is 12. 1/3 times 12 is 4. Put that here. Negative 4 plus 4 is 0. I can now write my polynomial as m minus 1/3 times 3m squared plus 6m plus 12. Quadratic formula on this guy gives me m equals negative 1 plus minus root 3i. So now I have a root, 1/3, right? A 1/3 is one of my roots. This is m1. And then m2 and m3 come from this pair. So I get a real root, c1 e to the 1/3 x, plus a complex conjugate pair, e to the alpha x, c2 cosine beta x, c3 sine beta x. This is like as complicated as it gets, right? Okay, here's another example. Third degree linear equation with an initial, so this is an initial value problem. It's going to be the same, right? You're going to get all the way down here to the general solution. And then, once you get here, you're going to use the initial values to pin down C1, C2, C3. So we get m cubed plus 2m squared minus 5m minus 6 equals 0. That's my auxiliary equation, right? I need to find the roots. Possible roots are plus minus 1, because this is a 1 out front, we get plus minus 1, plus minus 2, plus minus 3, plus minus 6. Those are the roots of the last term. Sorry, the factors of negative 6. We can check them down the list, and we find out that m equals positive 2 works, right? So we're going to divide this polynomial by 2, bring down the 1. 2 times 1 is 2, put that here. Add these up to get 4. 2 times 4 is 8, put that here. Add these up to get 3. 2 times 3 is 6, put that here. Negative 6 and 6 is 0, so I get this polynomial should be equal to, right, m minus 2 times m squared plus 4m plus 3. And then you can factor this, pretty straightforward, m plus 1, m plus 3. So I get 3 distinct real roots. Yg of x equals c1 e to the 2x, c2 e to the negative x, c3 e to the negative 3x. And now I just use my initial conditions, right? My first initial condition is that y of 0 is 0, which means c1 plus c2 plus c3 is 0. Y prime of 0, I take derivatives everywhere. Take derivatives, right? I get 2c1 e to the 2x plus negative 1 c2 e to the negative x minus 3c3 e to the negative 3x. And I plug in 0 for x. And I get 2c1 minus 1c2 minus 3c3 equals 0. And then I take another derivative and plug in 0, and I get 1. And I get these 3 equations. Now I'm solving a system of 3 equations in 3 unknowns. Pick your poison, right? The general method is to use the first equation to get rid of the c1s in 2 and 3, right? Obtaining 2' and 3'. And then we can solve 2' and 3' for this pair, c2 and c3, and then go back to 1 to get c1. So here's what you do. You take 1, right? You're going to add, I'm going to take negative 2 of this equation and add it to the second equation, right? I'm going to take this equation times negative 2, and I'm going to add straight down. And then I'll get 0c1 minus 3c2 minus 5c3 equals 0. Right, so I'm going to multiply equation 1 by negative 2. Negative 2 times equation 1 plus equation 2 gives me this. This is my 2'. Again, I'm going to try to eliminate the c1s, right? Negative 4 times equation 1 plus equation 3 gives me this 3'. And now I'm left with this pair of equations, 2' and 3', a system of 2 equations and 2 unknowns. I'm going to eliminate c2, it looks like, right? Multiply the first equation by negative 1 to cancel out the c2s. Negative 2' plus 3', right? Gives me 9c3 equals 1. So c3 equals 1/9. Great. Now I take this and I plug it into, it doesn't really matter, right? Plug it into 3'. Why not? Plug it into 3', right? Negative 3c2 plus 4 times 1/9 should be equal to 1. Huh. I think I messed this up here. There should be a plus 1 on this side. Yeah, this looks wrong. This looks wrong. It's embarrassing. I've been using these notes for a while, right? Okay, let's get rid of this. There should be a minus 1 here. So this gives 4 over 9 minus 1 is negative 5 over 9. Divided by 3 is negative 5 over 27. Okay. Now we go to equation 1, the original equation 1, right? Yep. Okay, back to equation 1. Minus C2, so this should be plus. This should be plus 5. Over 27 minus 1/9, which is multiplied by 3. So this is positive 2. Should be positive 2. 2 over 27. Okay, so this should be plus 2. This should be minus 5. Minus 5. Sorry about that. Okay. Okay. Anyway, the point is you can solve this system of equations, right? And you get your general solution. We'll pick up on section 4.4.